Hello?
Hello.
We can hear you, Franco. What you want to contribute to the convo?
Oh no, I just have a question for Witsit. I tried to tweet it in previous days. I'm not going to discuss a lot the atmospheric physics because I'm not an expert in that, but it's just a matter of understanding what he says, because he uses some terms that I'm not used to, like equipotential lines and like Gaussian surfaces. At least I know I'm used to speaking of equipotential surfaces, not lines, and I know what a Gaussian surface is, but I don't see what he means in that specific case, saying that a uniform electric field needs two Gaussian surfaces. To me, to my knowledge, a Gaussian surface is a mathematical surface which is closed one, which you take to compute the flux of something like some field, like an electric field. But then it can be a cube, it can be whatever shape, and it's just mathematics, it's not physics. It's just meaning it's not a physical surface, it's a mathematical surface. And if he means that there have to be two, say, plates, like in a capacitor, to generate a uniform field, I'm sorry to say that that's not true, because in electrostatics, if you take a uniformly charged plane, infinite plane, that produces a uniform field on each side, and that is with only one physical thing, which is it's an infinite plane. And also you can have a spherical capacitor made with just one conductor. You could charge a metal ball uniformly, and that produces a field that is perpendicular to the metal. It is not uniform. It is uniform when you're very close to the surface, but that does not need a second plate. Okay. And you have infinite Gaussian surfaces, because any three-dimensional volume in space has got a border, and the border can be defined as a Gaussian surface. So I don't know what he means. I'm just asking what he means by that.
Okay, that was a lot, but it's all good. So yes, you're right. Like when it comes to the concept that's used in Gauss's law, it's a mathematical concept, right? A Gaussian surface, and it's just a closed surface in three-dimensional space. But just saying that it's not physical and we can just pick any random place and then draw a hypothetical shape is not reality in any way. To actually replicate equipotential lines, right? Which you asked me what I mean by that, but it's very simple. It's just like the regions in the field where the electrical potential is the same. And to actually replicate this in physical reality, you have to have two physical surfaces acting as your Gaussian surfaces. For example, I've done it with two metal plates. And like I said, I actually flipped the polarity using a Van de Graaff generator to show that I can get objects to levitate or really just rise up to the other side of the plate once you flip the polarity of the field, as if to show the analogy of the Earth, because ours is down, right? But anyway, the point is that to actually show this in reality, you would need two physical Gaussian surfaces, two physical plates seemingly acting as Gaussian surfaces, and the field's perpendicular to that. You then said, well, then if you have an infinite plane, so your original critique was that it was conceptual, but then you brought up an infinite plane, which obviously you're not testing or replicating in any way. That's merely mathematical. But in addition to that, you then brought up a sphere, and you said that it would be equipotential close to the surface. Like, well, no, it would actually not be equipotential anywhere, right? Like, because it's not perpendicular, it's a curved surface, and that actually proves my point, right? Which when you invoke the sphere and you said that it would only appear to be somewhat equipotential towards the surface. Yeah, that's the problem, right? Because you actually need two Gaussian surfaces, and it needs to be perpendicular to the vertical field that we have on the Earth. So My point is, yes, it is a mathematical concept that is used in Gauss's law, but the point is that to replicate it in reality, you need two real physical Gaussian surfaces, right? So that's the only way it can be shown. So until someone can show me in reality that you can have equipotential lines in an electric field without having these two effectively metal plates, typically perpendicular to the field, then it's just a baseless claim. It doesn't exist because I've actually gone to test it, and you have to have. You can use like freaking pizza trays. It doesn't matter what you use, but I've had to test it, and you need the two physical surfaces. So I think that was most of what you said there.
No, not really, because again, it's not equipotential lines, but it's equipotential surfaces. And for a sphere, if you take a charged sphere, it has equipotential surfaces, which are concentric spheres. There are potential surfaces for any electrostatic field. There are equipotential surfaces which are defined mathematically, meaning there are sets of points in space where the potential is constant, is got the same value. If you take two plates, if you make a capacitor with two metal plates which are not Gaussian surfaces, because Gaussian surfaces have to be closed surfaces, those plates, as I said, you can just have one plane, and it has to be infinite in order to produce a uniform electric field. But if you take two finite plates and make a flat plate capacitor, then you will have that the uniform is the field is approximately uniform at the center of the plates, away from the borders, but at the borders it's not uniform. And that's precisely what you do when you solve physics problems, saying that you are approximating the plates as infinite, because otherwise the field is not uniform. So even if you do it in reality, if you measure the field at the border of those plates, it will not be uniform. Sorry. This is electrostatic theory, which is very, very well understood.
Yeah, so I've specifically addressed this in my show when people ask, which is, yeah, in theory, there would be some type of differentiation towards the outside. Conveniently, we can't go there, huh? And you don't have infinite anything in reality. It's just a mathematical concept, and you don't have any planes. You don't get to invoke a plane, right? So we have a plane, and we have equipotentials that are parallel to the surface of the plane Earth, and we have a vertical electric field. And so if we have two parallel Gaussian surfaces, which again can be replicated, that will give you the finite volume needed to have these. I call them equipotential lines. You don't have to agree with it. You can call it surface if you want to, but they are parallel horizontal lines for the actual construct mathematically anyway. So my point here is very simple, right? Sure, you have to treat it as infinite to make it like equalized throughout the entire thing, but we can't even get out to the extremities to know what the electric field is actually doing there. And the real problem is that you can't even get the equipotential lines in the vertical field replicated in any way with a sphere without the second Gaussian surface. The only way to replicate it in physical reality, which is what we're concerned with, is to have two physical Gaussian surfaces.
I disagree again, because again I don't know what you mean by Gaussian surface, and that's if you mean two metal bodies, two conductors, no, it's not needed. You take a spherical metallic object. You take a spherical globe, and you charge it. The charge will spread uniformly, and that will produce an electric field which will go as 1 over r square. But if you go very close to it's exactly as it's the same as the gravitational field. The same dependence on distance. And if you go very close to the surface, it will be almost uniform, and it doesn't need any second plate to produce. and that that's basically what is in Van de Graaff generator, something like that. You have a charged ball, and it produces an electric field which is very close to uniform, close to the surface, and it doesn't need a second plate, and it has equipotential surfaces which are concentric spheres. That's simple electrostatics. I'm sorry.
No, okay. Again, though, with the sphere, it isn't going to maintain the equipotential characteristic anywhere right off the surface, right? It's going to drastically change. The reason is simple, because you don't have finite volume. In order for the system to equalize out and give you the equipotential, you need finite volume. In reality, to create finite volume, you need physicality, right? So again, yes, in terms of Gauss's law and the mathematical construct that we use, you can use hypothetical surfaces, blah, blah, blah. In reality, you would need a real physical surface, right? So a closed 3D surface giving you the finite volume. The reason that you have to keep on adding the caveat of close to the surface is because it wouldn't maintain that equalized state or the equipotential distribution, right, as you got further off the surface, because there is no finite volume. The reason the math shows us this is because it's based upon the behavior of electric fields, right? So now I went and tested it, and I'm saying no one can replicate a vertical electric field with equipotential the way that we observe it on the Earth, right? And that's as high as we can individually validate, by the way. You have to start making up claims about going to space to even challenge that. What we see on the Earth is equipotential up 100 volts per meter all the way up. And in order to actually replicate this vertical electric field with equipotential distribution, you have to have two physical surfaces perpendicular to the field, seemingly parallel to one another, parallel to the surface, right? And now the Earth's surface would be acting as the initial plane. Then you have parallel horizontal equipotential lines going up. Then you would have a parallel surface above. I replicated this, and it absolutely works. So in order for the globe to explain phenomena that we actually observe, someone's going to have to demonstrate to me in physical reality that you can have that phenomena without a second physical Gaussian surface. Basically claiming it doesn't mean anything. The example you keep bringing up makes my point, which is that it actually doesn't work, right? Because as you come off the surface, it's not equipotential. But we do see its equipotential off the surface on the Earth. Good. Did he cut out or did I cut out?
No, I think he cut off. Frank, are you still there?
He dropped down to the listener. I think his mic went out or something.
There are equipotential surfaces, as I was saying. You take a sphere, 6,400 kilometers, and then you take a sphere 600 and 400 and 401 kilometers, right? It's very tiny difference. It's a very small percentage difference in the radius. But even if you take a sphere which is twice as big, all concentric spheres are equipotential surfaces, and you don't need any physical surface to obtain that. It's just electrostatic. I'm sorry, but electromagnetism is very, very, very well established. Otherwise, your devices would not work. You don't get to contradict electromagnetism. It's very, very well established, and electrostatics is something that the whole world agrees with.
Yeah, okay. Yeah. That's my point. Which, for one, you don't have concentric spheres in your model, unless it's just mathematical concepts. Secondly, I agree, it's very well established, and that's my point. I've replicated it physically with the Van de Graaff generator, flipping the polarity of the field and changing the vector of the object.
We make experiments with capacitors and things like this in every high school and every university when you teach electromagnetism. So we know it works, of course. But that doesn't mean that it cannot be done with a sphere. And the fact that there's an electric field which is nearly uniform as close to the sphere does not mean that you need two surfaces. And even if you needed a surface, For instance, I don't know. I'm not an expert of atmospheric physics, as I said before, but it can be just, for instance, a cloud. What happens in thunderstorms? You have a sort of layer of clouds which have a different potential with respect to the Earth, and then discharges happen. But then your second surface that you desperately need is just the clouds. But it's not needed. In order for an electric field to be established, you don't need two metal surfaces. You don't need them.
First of all, the bottom of clouds.
Guys, this conversation you guys are having, it make sense to have it kind of like separately, because I feel like we're going down a rabbit hole here.
Hold on, Prometheus. I don't know if you noticed, but Sacred and I are the hosts of this space. They are having we are enjoying this excellent build going on. Appreciate that concern. If there are any listeners who might be a little confused as to what we're talking about, feel free to allow us to slow it down, because we have been doing this for 79 weeks, so we do have to go back and break things down. But y'all carry on.
Yeah. So first of all, the bottom of clouds are actually flat. I'm not sure if you're familiar with that, but it doesn't really matter, because you can't just basically say that you can have it on a sphere over and over. You're going to have to physically replicate it. That's the way that science works. I verified my claim with a scientific experiment, a naturally observable phenomena. I then varied the independent variable and verified the actual causality of vector of objects, which gives us an actual demonstrable experiment showing us gravity, quote unquote, and the determination of the downward preference on a flat Earth. What I need you to do is show me equipotential filled, right? A vertical field with equipotential on a sphere without a second Gaussian surface. The reason you can't do that, and you've admitted it, you say, oh, it works close to the surface, is because you can't maintain the perpendicular nature of the surface. Meaning, very simply, for everyone, the Gaussian surface has to be perpendicular to the fields. Okay, well, we have a vertical electric field on the Earth. So what is perpendicular to vertical? Horizontal. Now, the plane Earth acts as the bottom perpendicular surface. You have to have one above you that's parallel to that surface to give you the equipotential.
No, I'm sorry. This does not make any sense. I'm sorry.
Oh, it does. It makes sense. That's why
no,
you
it doesn't.
triggered.
No, it doesn't.
Yeah,
no, it doesn't. You have definition of the perpendicularity to any surface, as long as it's a double differential. You have a perpendicular to a toroid. To a toroid, you have perpendicular. You can define perpendicular to any.
Of course, Franco.
And yes, a radius is radial direction is perpendicular to a sphere. And
only at one point. Only at one.
Yeah. Okay. What's the point with that?
Because that's not what we see in reality. What we see is across the entire Earth, we have a vertical electric field with downward electric current of 10 microamps per square meter.
Yeah, but vertical means perpendicular to the ground, and the ground can be a small proportion of a spherical surface. What's the problem with that?
Okay, first of all, answer this question. What is perpendicular to vertical?
Depends how you define vertical, because you have perpendicular. I can define what is perpendicular to my cup of coffee that I have in my hand at this moment.
It'll be an angle. It'll be an angle that's not vertical. I asked you a simple question.
This is mathematics.
What is perpendicular to vertical?
Perpendicular is. But this is just semantics, right? Perpendicular to vertical is. You want me to say horizontal? Yes, but
I want you to say the right answer. That's right, Franco. Okay.
No, because what is vertical? What the fuck is vertical?
I'm not trying to have bad faith, dude. So just calm down.
What is vertical? What's the definition of vertical?
For you, it's just vertical relative to the center of mass. Okay, so if you'll calm down,
Franco, chill. Relax. Take a deep breath. Take a deep breath. Take a deep breath.
I'm
Don't
not
get fired up.
Franco, I'm not trying to have bad faith with you. I understand you think I'm just being semantic and being like, ha, I got you. You said horizontal. I'm not. Your position is that even on a sphere, right, that particular point of the surface would be perpendicular to the locally established vertical. It's the same as plumb lines with surveying.
Yeah.
I understand that. The problem is, though, that the field can be measured beyond a single point. It can be measured over immense distances, right? And it maintains horizontal from that point, and all of the equipotential of the field increases parallel to that. That the extension of that horizontal baseline and the extension of the subsequent parallel lines is the part that doesn't work for you. And the lack of a physical surface perpendicular to the field above you shows that what we observe on the Earth cannot work.
No, I don't agree, because I'm not following this. If your problem is defining a perpendicular to a surface, that is defined anywhere. It's a mathematical definition, and anywhere it can be perpendicular. If you are wanting to see this experimentally, just take one. The fame you see them on YouTube videos, because you guys like so much YouTube videos. You have videos of spinning water on a merry-go-round, something like that. And the shape of the spinning water is parabolic, and at any point the surface of the water shape is perpendicular to the apparent field that is felt there, which is just the direction of the total force acting on any single element, volume element of water. So you have something that is demonstrably a parabol, and a parabol is because it is a surface that is locally perpendicular to the expected force field in that point. So you can do it. You can see that things physically adapt so that they're locally perpendicular to a force field, and this is done with everything, not just with uniform fields, with everything. You define it mathematically. You define what an equipotential surface is. For forces which emit a potential, you have equipotential surfaces, and locally, the field is perpendicular to the equipotential surface. This is a mathematical relation, which is the gradient of a scalar function is always perpendicular to the equipotential to the level surfaces. Okay. So this is known. This has been known for centuries. Like, this is simple mathematics, and it does describe physics. But if your point is that you cannot define what perpendicular is, if it's a sphere, this is not a problem.
That's not what I said. Why are you straw manning me when I got out ahead of it, and I actually still manned your position as to what perpendicular is to a local point? And you went on this diatribe about how I'm being somehow semantic in bad faith. I'm not. Please don't interrupt me. It's very simple. This is the problem that you have, okay? So we go up 100 volts per meter. Okay, now these are parallel horizontal lines. Every meter we can draw a horizontal line. And we're going to go up another meter, draw another horizontal line. These lines extend all the way out. So now,
how do you know that?
Wait up.
How do you know that
because,
they're perfectly?
Because I'm about to show you how we know that. So, okay, we can measure the potential even with the voltmeter. Okay, so we have 100 volts per meter, and it's perpendicular. We have a vertical field, and the Gaussian surface is perpendicular to that. Now, here's the point. Say we go up to we go 5,000 meters up on a mountain. Okay, here's my question for you. If I measured the potential at 5,000 meters on a mountain, and then you go 1,000 miles away and you measure the potential at 5,000 meters on a mountain,
yeah,
are we going to get the same value?
I think so, but it depends what your model is. But anyway, it is.
Okay.
But it
Yes.
does not. It's not. It's, okay. So
we're gonna get the same value. That's your problem. On a sphere, you're not gonna have the Gaussian surface that's perpendicular to the vertical field separated by 1,000 miles. Okay, so you need a horizontal baseline and parallel equipotential lines perpendicular to parallel Gaussian surfaces to actually match what we see in reality, which is wherever your elevation is, which is a vertical distance above sea level, is always going to have the same potential extended all the way out, not just isolated to a singular point, which necessitates a Gaussian surface perpendicular to that above and below.
Sorry, but it's not true. But it's not true. If you are at a point in a sphere, the sphere is 6,400 meters, kilometers radius, and then you go at the radius that is that plus 5 kilometers, which is a very high mountain. Okay, and then you take another point, say at the antipodes. So you do it as a North Pole, or you do it in Italy, and do it in New Zealand, which is at the antipode in my model. Sorry, and then you get the same amount of potential difference. By the way, you don't measure potential; you measure potential differences. That's one very fundamental things. And then you measure the same potential difference, and it's not incompatible with the fact that these are the potential differences between two spheres, concentric spheres, and the fact that they're both the directions where you measured the differential the potential difference is along the radial direction, which is perpendicular to the surface, which is what you call vertical. It is not incompatible with spheres. You can have it both ways. You can have this kind of behavior on a flat plane, and you can have it on a sphere. It does not discriminate between the two.
That is incorrect. So, like I said to you, I replicated it myself. You would have to admit that if I had a horizontal plate, metal plate acting as my Gaussian surface, I could replicate a vertical electric field with equipotential distribution with a parallel horizontal plate above it, and I could go as high as I wanted to go. I could go forever. I could go 1,000
No,
meters.
you cannot go forever because it has to be at a height which is very small with respect to the size of the plates. Because as soon as you go to a distance between the two plates which is comparable to the lateral size, it will fail to be uniform. Sorry.
That's correct. That's correct. Yeah. But that's non sequitur. We're talking about the Earth.
Oh, no. You say you can go on forever. You cannot. Sorry.
Okay, you would have
to be infinite. It has to be an infinite plane in order to go on forever.
Okay, dude. Talk about semantics. You would have to go vertically.
Oh, I'm talking about mathematics and physics.
In order for that to actually apply to what we're talking about, which is the Earth, you would have to go a vertical distance. You would have to go higher than the Earth is wide, quote unquote, or whatever. Like however long the plane is of the Earth, you can go that high and have equipotential. Okay, so my point is that's the only limitation is the actual baseline itself. Now, for you, that isn't the case. If you have a sphere, right, and you try to replicate equipotential distribution of a vertical field, which it will only be vertical in relation to a specific point, perpendicular to a specific point, as you get further away from that surface, it will not maintain equipotential. Absolutely will not. You conceded at the beginning. It's just a fact that can be replicated in the lab that you will not be able to do that.
No, sorry.
In order to explain what we see on the Earth, you have to be able to do that. It's game over. No. Globe debunked. I'm sorry, bro.
No, I'm sorry. It's maybe sorry. It's not. If you have a sphere, if you go away from the sphere, if you go away from the sphere at a distance which is comparable to the radius of the sphere, it's true that the field will cease to be uniform, meaning that it will show a dependence of the magnitude of the field with the radius. But it's not true that you cannot have potential surfaces because every single spherical surface, which is concentric, which has the same center as the original one, as the charged sphere is an equipotential surface. You can also have an equipotential surface at distance like the billions of kilometers, right? It's still equipotential. I'm sorry.
Oh my gosh.
I know.
All right, we're going to wrap this conversation up. It's getting circular, dude. We're going to have to disagree here. You admitted yourself that if you admitted yourself that on a sphere, that it would only be uniform and have equipotential right by the surface, really close.
No. I did not say that. I said that. I said that. No. We're not understanding each other. What I said is that the field will be close to uniform as you go near the surface. But uniform field has nothing to do with the fact that equipotential surfaces exist, because equipotential surfaces exist for any electrostatic field. That's the definition of an electrostatic field, right? It's Maxwell equations. You have, it's derivable, it's expressible as a gradient of a potential, and any scalar surface, any scalar function has equipotential surfaces. So equipotential surfaces are defined for any electrostatic field, and in particular for a spherically symmetrical field, equipotential surfaces are all spheres which are centered in the origin of coordinates.
They're not spheres.
Yes, I'm sorry. This is the subject of what I teach at university, and I give exams.
That's embarrassing.
Okay, it's a fallacy because I know it's a fallacy because I'm appealing on authority. But
Can you allow Witsit to respond, Franco? You're just talking over him and then shouting.
I'm talking over him because I think I know what I'm teaching, and I'm.
Okay, hold on. Franco, you do gotta I don't mind the back and forth, right? We did this a couple weeks ago. Back and forth was cool. Sometimes we got to interject for clarity, but you can't interrupt because you don't want to hear what's being said. All right, I'm gonna let you finish your thought, Franco. I'm gonna let Witsit respond, and then kind of to wrap this up, what I want maybe to happen, Franco, maybe if you can steel man, let me know if you don't know what that means, if you never heard that term before. I want you to steel man Witsit's position on this conversation. Basically repeat back his position on what you guys are arguing about, just so we all know that you understand where he's coming from, and then maybe Witsit can do the same thing for you. So go ahead, finish your thought. I'm gonna let Witsit respond, and then we'll go into the steel mans, and then we'll move to the hands and maybe build on a different conversation or something else in depth. Maybe we can go from there. That makes sense, Franco? How about there's a little bit of a mute lag. Franco, you there?
Yes, I'm here. Sorry.
Okay, so did that make sense? Did that make sense? So just finish your thought. We're gonna go to Witsit, have him respond.
Okay. I'll try to be calm. The point is, the reason why I asked this is because what I heard in his arguments has some problem with what is the terms and the definitions we use in this kind of physics. Because, for instance, as I said, he uses equipotential lines instead of equipotential surfaces. He uses Gaussian surface in a way that is different from what we use in the field, right? So I wanted to have to understand what he meant. Now, the fact, what he says is that since if I understand his position is this, you can only produce a uniform electric field. Let's leave the equipotential thing aside, but I think his point is you can only produce a uniform electric field if you have two planar surfaces at different potentials, and which is known as a planar capacitor, or plane or flat capacitor. I don't know what that term is exactly, but it's a very simple exercise in electrostatics. Right, and my objection is this is not true, because even if you want to produce an exactly uniform field, you just need a one single plate, which has to be infinite. If it's not infinite, and the objection is you don't have infinite things in reality. True. And that what is being said usually is you need to be very large, and then you measure the field far away from borders, because you don't want to see what happens near the borders. But this is also true for a two-plate capacitor. This is exactly the same problem, and the field ceases to be uniform as soon as you go near the borders, both with a two-plate capacitor and with a one-plate capacitor. It's exactly the same thing. And the fact that this is not possible with a globe is the difference with having a planar with respect to a spherical capacitor is that the field is not uniform when you have a spherical object. And by the way, the sphere does not have the border problems, because the sphere is finite, but it produces a field which is 1 over r squared. And if you have if you go near the surface, the field will be nearly uniform, because this is true for any continuous field, right? So so I don't know what the objection is, because the fact that we measure a field that we perceive as uniform near the surface of the Earth does not mean that this cannot be an approximation of a 1 over r square type field, which is the same thing which happens with gravity. So, and the fact of the need of a second surface is not true, because this is not what electrostatic predicts.
Okay. I'm going to say my closing here, and then I'm going to tap out. I'm supposed to be building a website. Keep getting distracted. Okay. Very simple, bro. We have a uniform field on the Earth. Okay. And it goes up 100 volts per meter. It's measurable. Keep going up. We have a uniform field with parallel equipotential surfaces. I call them lines. It doesn't matter. Same thing, right? Now, the problem for you is that you cannot have this on a sphere, because like you said, it will be concentric spheres. Therefore, you're not going to have parallel equipotential surfaces. Ironically, though, you brought up parallel plate capacitor. That's my whole point. To actually replicate the uniform, like parallel equipotential surfaces like we observe and measure on the Earth, you need a parallel plate capacitor, for example, to replicate it in reality. And this includes a horizontal bottom plate that's physical, then the vertical electric field that's perpendicular to that, and then a parallel plate at the top that is, of course, parallel to the bottom plate and perpendicular to electric field as well. This gives you the uniform equipotential parallel surfaces, which you cannot have with concentric spherical equipotential surfaces, right? You will have a non-uniform field, and it's because of the radial dispersion of the charge in relation to the sphere. It is impossible. And you absolutely, for a fact, cannot replicate this phenomena in physical reality without two physical Gaussian surfaces that are perpendicular to the vertical electric field. That is the only way. So in conclusion, the only way to replicate what we see on the Earth in real physical reality with a test that's in real physical reality is to have basically something like a parallel plate capacitor with a physical Gaussian surface, a vertical electric field with equipotential parallel surfaces going up, and then another parallel surface at the top, Gaussian surface at the top, to create the uniform field that we experience in reality. It is the only way. Cannot happen on a sphere. Basically appealing to math and concepts and claiming it can happen and ignoring the fact that it would have to be non-uniform doesn't change it. It's just a fact. The concentric spherical equipotential surfaces because it's radially dispersed,
Mhm.
intrinsically being a sphere results in it being non-uniform, and you don't have a physical parallel surface above us in your model. Therefore, you have to appeal to concepts in math. We can replicate it in real physical reality and replicate the uniform nature of the field. So that's game, set, match, Franco. I'm sorry. Until you can come replicate it with a real test, it's just over.
Okay, so wait, but that was such a dope build. Right before we get to Prometheus, Franco, can you just do me a favor? And after having that back and forth with Witsit, building on this topic, can you tell us what Witsit's position is, regardless of whether you agree with it or not?
Not sure. Not sure I understand the question.
Okay, so basically what I like to do sometimes when we have like these honest bills, for the most part anyway, we all got a little bit of bias. But I don't think that you or Witsit is intentionally lying, right? So you guys are standing in your own positions. So just to draw some type of a common ground, I just wanted you to do for us in the audience, explain what Witsit's position is in regards to this topic, even if you don't agree with it. I just want to see if you, I'm not trying to disrespect you by saying understanding or comprehending. I just want to see if you get where he's coming from, even if you don't agree. Does that make sense?
In a way, I think as I said before, I think his position is we measure a uniform electric field on the surface of the Earth, and that is only possible if you have two parallel plates, two parallel equipotential plates, which are both of them planes, geometrical planes. This is his position, and claims. His claim is, since we observe a uniform electric field, neither of those two needed plates, can be a sphere. I think his position is this. My reply is that this position does not agree with physics. I mean, it's not, but okay, but I disagree with this.
Okay. Thank you, Franco. Witsit, can you tell us before you get back to building your website, multitasking and stepping on all these globe earthers, aside from Franco, because that was a great build. Do you agree or accept his steel man of your position, or is there something that you want to correct?
I mean, it's decent, you know. Yeah, we have an equipotential field on the Earth. It's the intrinsic radial nature of of a spherical electric field that doesn't allow you to have the uniform equipotential surfaces parallel. He didn't do terrible. He just then said that he disagrees with it, but it's just a fact, right? So it wasn't terrible. I know there's a bit of a language barrier. I think he understands for the most part. I don't know. I don't know. Like, we'll just keep going, I'm guessing, but like he's not specifying, like, it's just a fact that like the radial nature of a spherical electric field does not allow you to have a uniform vertical electric field perpendicular to the parallel equipotential surfaces. But yeah, it wasn't terrible.
All right, that's what's up. Hey man, y'all caught that in real time, bro. Y'all not gonna get this anywhere else. I appreciate Witsit and Franco for that, bringing y'all expertise to the space, allowing us to hear how that transpired. And maybe we can do a little bit more deep dive into this topic and revisit this in the upcoming weeks. Franco, if you're open to that, feel free to join up. You know Witsit is gonna be in here. But let's hear from some of the other speakers in here. I think we got a couple hands up. I think we got Prometheus was up next,